Welcome back to The Explainer. Today, we're taking a serious zoom-in journey, literally diving into the nanoscale. We're going to look at what happens when the classical laws of physics, the rules that govern our everyday lives, are completely overthrown. It's a place where everything you thought you knew about the physical world basically gets turned on its head.
So, I really want you to think about this. What actually happens to physics when things get impossibly small? Imagine shrinking down past the macro world, past the microscopic world of cells, and entering this absolutely bizarre realm. A place where particles just casually walk through solid walls, and where objects exist in multiple states at the exact same time. Now, I know it sounds like straight-up science fiction, but it is the fundamental reality of our universe at the nanoscale. Okay, let's look at our roadmap for today. We'll start with the rules of the nanoscale, then unlock some quantum phenomena, check out electron traffic and transport, explore the power of geometry, and wrap up with exactly why nanotech matters.
All right, part 1, the rules of the nanoscale.
The core premise here is pretty simple. Our everyday macro world plays by one set of rules, classical physics. But when you shrink materials down to the nanoscale, and we're talking just 1 to 100 nanometers here, their physical, optical, and electrical properties change dramatically. They completely ditch classical physics for a whole new set of scaling laws. And this really boils down to 3 main drivers: quantum confinement, tunneling, and massive shifts in surface-to-volume ratios. Let's break down what those actually mean.
Moving on to part 2, quantum phenomena unlocked.
So our first major concept is quantum confinement. You probably know that in bulk materials, energy exists in these continuous bands. Electrons can kind of just roam freely within those ranges. But when you squeeze particles down into nanoscale dimensions, you're literally restricting their movement. Because of this, their energy bands actually break down into distinct stair-step levels. They can be on one step or the next step, but absolutely nowhere in between. And because of this confinement, we get the quantum size effect. This is the fascinating reality that simply making a material smaller fundamentally changes its traits. I mean, without even touching the chemical makeup of a material, just by tweaking its size at the nanoscale, you can change its optical absorption, the exact color of light it emits, and even its electrical conductivity. It is wild to think that a material acting as a strict insulator at the macro scale can suddenly become this powerful conductor just because we shrank it down. Then there's electron tunneling. Okay, think about throwing a tennis ball at a solid brick wall. Classical physics says it bounces right back, right? It just doesn't have the energy to go through. But at the nanoscale, electrons can literally pass through potential energy barriers they classically shouldn't be able to overcome. They essentially just teleport to the other side. It completely defies our everyday logic, but this probability skyrockets at incredibly short nanoscale distances, which fundamentally changes how electricity flows. Oh, and it gets weirder. Let's talk about quantum entanglement. This establishes a really unique and honestly kind of spooky correlation between quantum particles. If 2 particles become entangled, they share a quantum state. Measuring or even just interacting with one particle instantly affects the other, even if they're separated by massive distances across the universe. There is literally zero lag. And this specific phenomenon, it forms the very bedrock of emerging tech like quantum computing and completely unhackable quantum cryptography. And rounding out the weirdness, we have superposition. This principle allows quantum systems to exist in multiple states simultaneously. So a particle isn't just up or down, it's not just a 1 or a 0, it is truly both at the exact same time, right up until it interacts with its environment. The length of time it can actually maintain this super delicate multi-state existence is known as its coherence time. And right now, maximizing that coherence time is, for sure, one of the biggest hurdles in quantum physics today.
All right, part 3, electron traffic and transport.
So, imagine driving down a perfectly empty, multi-lane highway with absolutely 0 obstacles. That is ballistic transport. This happens when the mean free path of an electron, which is just the distance it can travel before hitting something and scattering, is actually longer than the entire nanostructure itself. The electron just shoots straight through without bouncing off a single thing. The result? Incredibly low electrical resistance and just massive conductivity. Now contrast that empty high-speed highway against what actually happens in our everyday macro-sized devices. That's diffusive transport. Diffusive transport is basically bumper-to-bumper rush-hour traffic. Electrons are constantly bouncing off atoms and impurities, scattering in a million different directions. But at the nanoscale, by engineering structures small enough, we can actually eliminate that traffic jam entirely.
But to manage that kind of flow, we still need traffic cops. And that brings us to the Coulomb blockade. In systems with extremely small capacitance, like a quantum dot for instance, adding just a single electron causes a massive spike in electrostatic energy. This single electron acts like an incredibly strict bouncer at a club, physically repelling and blocking any further electrons from entering. This is huge, because it allows us to control the flow of electricity with unprecedented precision, literally one electron at a time. And interestingly, this effect works best at super low temperatures, because too much thermal heat can actually give electrons the energy they need to push right past the blockade.
Moving on to part 4, the power of geometry.
A really surprising mathematical reality starts taking over at the nanoscale. As an object shrinks, its volume, which scales by the radius cubed, disappears way faster than its surface area, which scales by the radius squared. So because of this math, the surface-to-volume ratio is proportional to 1 over the radius. Simply put, the smaller the particle gets, the higher the percentage of its atoms that live directly on its surface.
And because so many atoms are suddenly totally exposed on the surface, surface-dependent properties just absolutely explode in intensity. Take gold, for example. Bulk gold, like the ring on your finger, is famously unreactive, right? It doesn't rust, it doesn't tarnish easily. But gold nanoparticles have such a high surface-to-volume ratio that their surface energy completely dominates, and they suddenly become incredibly active and potent chemical catalysts. It's a total 180.
And hey, it's not just size we're talking about. The literal shape completely dictates the physics here. A gold nanosphere interacts with light completely differently than a gold nanorod, totally shifting its optical properties. Meanwhile, the actual curvature of a nanomaterial heavily influences its surface tension and can drastically lower its melting point. Geometry even causes phonon confinement, which fundamentally alters how heat moves through the material. Plus, atoms sitting on sharp edges or corners of a nanostructure, they are way more reactive than atoms sitting on flat surfaces. At this scale, the physical geometry literally rewrites the materials rulebook.
Finally, part 5, why nanotech matters.
So what does this all mean for us? The crucial point is how we actually harness these bizarre rules to build revolutionary tech. That electron tunneling we talked about, that allows us to build scanning tunneling microscopes, letting us literally image individual atoms. Ballistic transport? That's the secret sauce behind ultra-high-speed carbon nanotube transistors that are set to revolutionize electronics. Entanglement and superposition form the backbone of quantum computing, promising processing power that's basically unimaginable today. And that bouncer effect, the Coulomb blockade, is exactly what enables precise quantum dot devices and single-electron transistors. We are taking the absolute weirdest bugs of the quantum universe and turning them into incredibly powerful features.
Which leaves us with one final thought to chew on. We are truly just scratching the surface of what the nanoscale has to offer. As we continue to master things like quantum confinement, entanglement, and the absolute power of geometry, how will we harness these unseen quantum powers next to completely reshape our macroscopic world? Thanks for joining me on this explainer, and keep questioning the rules of the world around you.